So discussing these diffuse rings, if they're not so well defined, their boundaries are hard to detect. Well, what's the best way to get images of these diffuse rings? So in the problem setup, let's say you're sending a spacecraft out there, they're flying towards the planet, and you want to get the best images, or at least the best chances of getting pictures of the diffuse rings. When do you start taking your pictures? What's the best time to do it? As usual, go ahead and pause, think about your answer, and come right back. So this one, there are arguments that are good for all of them. Let's start at the top. As you are approaching the planet, you're going to have the widest angle, the widest range of possibilities. And you can zoom in and use pictures, your previous pictures, to kind of focus on where your next picture should focus. As the spacecraft passes, you could turn around and see glow from the sunlight behind it, and maybe that'll help you. Or say your spacecraft and just put an orbit around the planet. This gives you the most time. Instead of imaging the planet, you look out towards the cosmos and try and find those diffuse rings. And the last option, doing your closest flyby. Perhaps you're going to be lucky and your spacecraft literally flies through the diffuse ring and can image some of it. So there are good arguments for all of these, but I'll tell you that the best time is as the spacecraft is passing the planets. Let's talk about this during the closest flyby. That's not going to work. We have these images in our head of these rings being really dense, but if you were to go into the ring, you would be very far apart from other particles. They're dense on a cosmic scale, but on the size of a couple of meters, there are still big distances separating all the different particles, even in the dense B ring of Saturn. So here's that backscatter effect, right? And as physicists, we gotta use a little kitty cat to show things off. The sunlight is behind the cat, and the light is coming in, hitting the diffuse parts of this cat's hair and scattering around, causing the outer edge to glow. Well, same thing when you want to try and image things like the G rings, these diffuse rings. You use backscatter effects of sunlight hitting these particles and bouncing in random directions to get your image. So shifting away from Saturn, here's a picture of Jupiter's rings. So the big shadow here, that is Jupiter, with the sunlight behind it being blocked out. And we're seeing a backscatter through the upper layers of Jupiter's atmosphere, and the backscatter highlighting the ring of Jupiter. So the rings in the other giant planets are mostly narrow and definitely diffuse. Switching over to Neptune. Neptune has 5 rings that are characteristically defined by these ring arcs, and this is a picture of the ring arcs. Basically what's happening is that the particles in the arcs are clumped together, and we're not really certain why. We're not certain what gravitational effects could be keeping them together. Any naive model that we write would actually predict that these arcs would disperse, and that you wouldn't be able to find these darker bands within the rings of Neptune. Uranus rings are very opaque and difficult to see. These images up here on these outer edges, you're seeing a lot of just scattered noise in your camera, and very difficult, but you do get to see the ring around Uranus. Here it is in better view, taken from another image 2 years later. So the things that we notice about the rings in Uranus is that the particles are tiny. The biggest ones are only about 20 meters in size. So they tend to be on the centimeter size scale. And from what we can tell is that these rings are very young in terms of planetary timescales, only within the last 600 million years old. Probably a moon that fell into the tidal limit of Uranus and was just immediately obliterated. So stitching all this together now, the colors, the darkness, the opacity. Here's what we can say. Saturn's rings are bright because they're mostly made of water ice. Nice. And that ice does a really great job of reflecting light, making the colors we see. And in fact, the mass of Saturn's bright rings is about that of a small icy moon. This will be an important fact to us that we're going to start trying to calculate in the next slides. Whereas Uranus and Neptune have these dark rings, probably of organic material. And once again, by organic, we just mean that it has a lot of carbon present. Organic just means carbon-based molecules. Now, why would the carbon-based stuff be dark? Well, here's a nice chunk of graphite, and as you can tell, it's very black material. It's a very dark substance. Carbon, and kind of a natural, any more relaxed state, not compressed down to diamond. That's a different topic. But carbon in this lower pressure state just makes these weak bonds that do a really great job of absorbing light, and it gives it its characteristic dark or black feature. Finally, Jupiter's rings, they're not as dark as the ice giants, but they're also not as bright as Saturn's. So the most likely scenario of Jupiter's ring is that it was more of silicates, rocks, instead of these organic compounds being broken away. Let's set up a new type of problem, and let's try and ask ourselves, how massive is the rings of Saturn? So let's take some facts and observations. Astronomers have looked out there, and we've found approximately 8 times 10 to the 19th particles. So there are 10 to the 19th particles floating around in the Saturn's rings. We know they're composed of these ice and rocks, and combined together, we'll say that the average density of this material is 910 kilograms per cubic meters. And the average little particle has a radius of only 4.5 centimeters. So with that information, we can ask ourselves, what is the total mass of a ring of Saturn? So the way to approach a problem is to start with the things that we can easily set up either through words or up here through a simple expression, and work it out step by step. So our goal is to figure out the mass of the total ring, and we can think of a ring of Saturn as just being a bunch of little particles distributed throughout one radius. So the total mass will be the number of particles times the mass of one particle. Assuming all these have about the same mass, every particle has about the same mass, then the total mass of the ring will just be n times the mass of one little particle, the lower m. So now I have to say, okay, what's the mass of just one particle in this ring? Well, we're going to table this expression off to the side and zoom in. We'll focus on one particle. Now, in reality, these particles are going to have weird oblong shapes. These are going to be just random scratches of rock or ice with different chips in there. So we'll make an approximation to simplify the problem, and we'll just say, hey, on average, this weird oblong shape is a sphere of radius r. Yes, this is an approximation, but what will show us that it's a reasonable one. It works out. It gives us a answer that we feel confident in. So with that, we know the density of this material, and you can just say, hey, density is just the ratio of how massive something is divided by its volume. In equation form, we'd say, look, rho, the density of the object, is the mass of the object divided by its volume. And the volume is conveniently, for a sphere, 4/3 pi r cubed. And this is the reason why we made this approximation up here. I'm just saying, hey, one tiny ring or one tiny particle is about a ball, about a sphere. So let's start stitching this together. The mass of just one particle, presumed to be spherical in shape, is just going to be its density times the volume, or rho times 4/3 pi r cubed. A reminder, r, the size, was that 4.5 centimeters at the beginning. Now, we could calculate this, but my answer is going to be, why bother calculating this? We want to know the mass of the total ring. I don't particularly care about the mass of one grain of dust. I want the whole picture. And from the equation that we set up before, way back in the beginning in just words, the number of particles times the mass of one particle gets us the total mass of the ring. So we'll take our expression, our rho 4/3 pi r cubed, and just substitute into the tiny mass term. And we'll get our end result, that the total mass of the ring is this product, number, density, volume of a sphere. So let's pull our numbers out from before. Pull them out from the beginning of this setup, where we said, hey, there were 8 times 10 to the 19th particles. On average, they have a density of 910 kilograms per cubic meter. All in volume of 4/3 pi. Have to get our units right. We initially said it was 4.5 centimeters, so we have to shift the decimal places to get into meters. So it's 0.045 cubic meters, or meters cubed. All said and done, and we get this reasonable result, this 2.8 10 to the 19th kilograms. So to put this number in perspectives, first, this turns out to be an underestimate of the accepted values. We made some rough approximations. One, that little specks of dust are actually balls of dust, and that the density and radius is uniform across all of these. But it does get us in the ballpark. The accepted value is a little bit higher. It's closer to 3 times 10 to the 19th kilograms. So let's put that number in scale here, because 10 to the 19th kilograms means nothing to my brain. I don't know what it does for your brain. So let's do some comparisons. Hyperion, another moon of Saturn, has a mass of 6 times 10 to the 18th kilograms versus the rings of Saturn, which 10 to the 19th. Luna, our precious moon, is on the scale of 10 to the 22nd kilograms. So altogether, I would say that the rings of Saturn has the mass of a intermediately sized moon, and it's composed of the same types of materials that we found in moons. And this is what leads us to believe that the rings were in fact a former moon. A moon due to whatever gravitational effects came too close to Saturn and got tidally ripped apart.